So let's take a look at determining the Lewis structures of carbon dioxide and oxygen difluoride. Valence electrons are the key for this, so the first step is to figure out how many valence electrons are in each of the atoms in the molecule. Let's take a look at carbon dioxide first. Carbon is in group 14 and has 4 valence electrons, the S's and the 2 from the S's and the 2 from the outermost P's. So carbon has 4 valence electrons, and each oxygen has 6. It's in group 16. So for carbon dioxide, we've got a lone atom there. The carbon is by itself, so that'll be in the middle. And we know that it's got 4 valence electrons. Each oxygen has 6, and I'm going to write the 2 that are by themselves kind of facing towards the carbon, because I know that they're going to be sharing electrons with the carbon. So carbon's going to share 2 of its valence electrons with oxygen, and oxygen's going to share 2 of its electrons with carbon, and that'll happen on each side. So what we end up with is carbon's 4 valence electrons get shared on one side with oxygen and on the other side with the other oxygen. So 2 of these electrons are from the oxygen, 2 of these electrons are from the carbon on each side. Total of 4 electrons being shared, 2 pairs are being made, and oxygen still had 2 valence electron lone pairs that were not involved in the bond. So these 2 electrons got shared with the carbon, which shared 2 of its electrons. Those ended up in the middle. These 2 electrons got shared with the carbon, and they ended up in the middle. And then these 2 lone pairs are still on the oxygen. Now, we don't show the bonds with dots like that because that ends up being too many dots. So we're going to show these 2 pairs of electrons that are being shared as lines. And it just makes it really more clear that it's a double bond. The lone pairs that are on the oxygen, though, we still write those as dots. So the Lewis structure for carbon dioxide has 2 double bonds. They're being shared with the oxygens, and carbon has no lone pairs. All of its valence electrons got shared with oxygens, but each oxygen has 2 lone pairs. All right, so let's take a look then at OF2. This is a different beast because we've got different numbers of valence electrons. So oxygen still has its 6 valence electrons. It's got the S2s and then the P4s, so that adds up to 6. But fluorine now has 7 valence electrons. It ends in P5, so the S's, the 2 S's, and then the P5s adds up to 7 valence electrons. So that makes things a little different. Now we still have oxygen all by itself, and it's the lower electronegativity, so that goes in the middle. And remember, it's got 6 valence electrons. And I'll have the extra ones, the ones that aren't filled right now, on the outside. And then 2 fluorines. And I'll put the one that's not got a pair with it kind of next to the oxygen because I can see where this is going. So you can see that fluorine wants to share its one lonely electron with oxygen, and oxygen has a nice place for that to go, and that happens on both sides. So what you end up with is oxygen sharing one of its electrons with fluorine, which is sharing one of its electrons with oxygen. It's a beautiful thing, and that happens on both sides. So there's 2 electrons in between fluorine and oxygen on both sides. One is from the fluorine, one is from the oxygen. And then oxygen still has its lone pairs that were not bonded, so the non-bonding electrons. Now, once again, we don't show bonds as dots, we use a line. So the final Lewis structure will show fluorine single bonded to oxygen, but fluorine has 3 lone pairs, and that's on both sides. And this oxygen has two lone pairs, two non-bonding electrons. So we've got oxygen single bonded to the fluorine, two lone pairs on the oxygen, three lone pairs on each fluorine, and we've got two very different kind of bonding situations, and it's all because of the numbers of valence electrons.